Howdy doody. Today, I want to look at one more way to evaluate limits, which is called the squeeze theorem. But before we get to the squeeze theorem, I want to look at a simpler theorem first. And I'm writing this a little bit because if I didn't, you might see this underneath the phrase the squeeze theorem and think that this is the squeeze theorem. But this is a preliminary theorem that we'll look at first. So all of that aside, let's take a look. If f of x is less than or equal to g of x when x is near a, except possibly at a, and the limits of f and g both exist as x approaches a, then the limit as x approaches a of f of x is going to be less than or equal to the limit as x approaches a of g of x. We can do kind of a very quick drawing of what this might look like. So here we have a graph of two functions, f of x and g of x. And remember, we're told when x is near a, f of x is less than or equal to g of x. So we're only looking near x equals a. We're only looking close to that value. So it doesn't matter that over here f of x is greater than g of x. We only care what's happening near the value a. And in this area, we know that f of x, the blue function, is less than or equal to g of x, the red function. And so this theorem says that the limit as f of x approaches a is going to be less than or equal to the limit of g of x as x approaches a. And I hope intuitively that makes sense. In this particular drawing, I've made it so that g of x is greater than f of x. They could be equal. These two curves could touch somewhere. But if we wanted the limit of f of x to be greater than the limit of g of x, then the graph of f of x is going to have to dip above the graph of g of x somewhere. This isn't a proof, just kind of a bit of an explanation. If this wasn't true, if the limit of f of x as x approached a was bigger than the limit of g of x, we would need this graph to dip above the other graph for that to be the case. So as long as f of x, kind of in this neighborhood of a, is less than or equal to g of x, there's no way for that limit to be larger than the limit of g of x. I hope that makes a bit of intuitive sense, because for the squeeze theorem, we're going to bring in a third function. So we're not just going to have the graphs of two functions, we're going to have the graphs of three functions. Let's take a look at that. So here we have the squeeze theorem, and it says if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, except possibly at a. Now what this means basically is that g of x is between f and h. We're saying g is sandwiched between f and h. Sometimes that's called the sandwich theorem instead of the squeeze theorem. But so long as g is between f and h, when x is near a, except possibly at a, and also if the limit of f of x as x approaches a is equal to the limit of h of x as x approaches a, so those outer functions have the same limit, we'll call it L, as x approaches a. The squeeze theorem tells us that means that g of x as x approaches a also has to have a limit of L. Now let me draw you a quick sketch of what this looks like. So here we have our graph, and there are three functions, f, g, and h. And remember, we only care what's happening around A. We could shade in this area again to show that, right? Because it doesn't matter that G is less than F over here. It's just in this neighborhood of A, when we're nearby A, we need g to be between f and h. So f is the lowest function, and then g is in the middle, and then h is a higher function. And so long as g is between f and h in a neighborhood of a, and the limit as x approaches a is the same for f of x and h of x, that means they kind of need to come together so that they have the same limit. They're both approaching the same value, which is actually L, right? That is the value of this limit. What that means is that the limit of g of x, which is in between those as x approaches a, also has to equal L. Basically, if g is stuck between h and f, and it could be doing lots of crazy things in here, but if it's squeezed in between those two, and h and f end up having the same limit, meaning they're both squeezing together and approaching the same value, that means that g has to share that same limit because it is stuck between them. And the reason that this ends up being useful is because sometimes g is a weird function and it's hard to work with. But if we can squeeze it between easier or simpler functions, f and h, such that all of these things are true, that will help us find the limit of g of x as x approaches a. Let me show you a classic example here so you can see where this is useful. Now here we're being asked to show that the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. Now we can't apply the multiplication property saying that the limit of a product is a product of the limits, because if we try and evaluate this individual limit, the limit of sine of 1 over x as x approaches 0, that limit doesn't exist. This is a problem we actually looked at earlier. We saw that as x gets closer and closer to 0, this was oscillating more and more, basically infinitely many times as x approached 0. So this individual part of the function, when we look at that limit, it doesn't exist. So we can't just take the two limits and multiply them together. Instead, we're going to apply the squeeze theorem. Obviously, that's what we're looking at today. And so we need to be able to squeeze this function in between two other functions that both have a limit of 0. And one thing that we can recognize here, if you look at sine of 1 over x, this quantity right here is always between -1 and 1, because sine of anything is always between -1 and 1. So that means this whole function is going to be between -1x squared and +1x squared. And so those are the functions that we can use as bounds on this. So we know that if f of x is -x squared and h of x is +x squared, then this function that we're looking at, the one that we want to find the limit of, is always going to be between those two, f of x and h of x, or equivalently -x squared and +x squared. That's because this sine of 1 over x is always between +1 and -1. Now, if we look at the limits of -x squared and +x squared as x approaches 0, those are easy to calculate. If we look at the limit as x approaches 0 of -x squared, that's a polynomial. We can use direct substitution, and plugging in 0 there, we end up with 0. And similarly, if we look at the limit of +x squared as x approaches 0, that's also a polynomial. We can use the direct substitution property, and we also get 0. And so because this function is always between those two functions, and both of these limits equal to 0, by the squeeze theorem, so the squeeze theorem says that the limit as x approaches 0 of the middle function, x squared sine 1 over x, has to also equal 0. So the squeeze theorem tells us that that limit is also 0. And what I want to do really quickly is I want to show you what the graph of this function looks like, specifically when it's graphed against f of x equals negative x squared and h of x equals positive x squared. So you can see the squeeze actually happening. So let me put that graph on the screen. All right, I know this is quite large and it's blocking everything else. So if you need everything else, you're going to have to rewind later. But this is a graph where this top parabola is x squared. The bottom one is negative x squared. And the one in the middle is x squared times sine of 1 over x. Now, we saw that sine of 1 over x without the x squared earlier, it oscillates between negative 1 and 1, and it oscillates more and more frequently as we get closer and closer to 0. And we do have the same thing here with these oscillations. They're getting more and more frequent. But because it's being multiplied by x squared, instead of going up and down between positive 1 and negative 1, this is actually oscillating between positive x squared and negative x squared. And so even though it's oscillating quite a bit in the middle, it's getting pinched by these two functions, so that even though it's oscillating an infinite number of times in there, it's not oscillating any distance because it's being pinched down to a point right there in the middle. So in the end, it's being squeezed by these two upper and lower functions, and that's what causes the limit to exist and be equal to 0, because there's nowhere for it to oscillate when it gets pinched together like that. In particular, the squeeze theorem is useful when we have something weird with a sine or a cosine of something difficult, where we have this kind of erratic sort of oscillation, but where there's also a factor that pinches things together so that even though it's oscillating a ridiculous amount, it's not oscillating any distance, any real distance at the point that we're looking at.